Hello, everybody. Welcome to this session. Thank you for choosing to invest the next 45 minutes of your life with me in this room. I appreciate that. My name is Daniel Moth, and 3 years ago, I moved from Microsoft in the UK to Microsoft in the US, and specifically to join the parallel computing platform, which delivers various technologies into various Microsoft products. So for example, in Visual Studio 2010, we released the parallel patterns library and the concurrency runtime that enables C++ developers to take advantage of multi-core systems. We also released in the same Visual Studio 2010 the task parallel library, TPL, that enables the same capability for .NET developers. Now, both of those have unparalleled support for parallel debugging. There's no pun intended there. In Visual Studio, and that parallel debugging is actually my area of focus that has been for the last 3 years. And it's only less than a month ago that I switched focus from the parallel debugging to this new C++ technology that enables developers to take advantage of the GPU. So at this point, maybe I should check how many people were in this morning's keynote, the Herb Saturday. Can I have a show of? I knew that was going to be a stupid question. Let me ask a different one. How many people in here were not in Herb Saturday's keynote? Don't be shy. OK, so that's like 4 people. So for the 4 of you, what we've done today is we've announced a heterogeneous platform support in the next version of Visual Studio. And this is a technology that we're calling C++ AMP, a C++ accelerated massive parallelism. It's a great product to work on. Has the word massive in it, I think. So C++ AMP. And what we did at the keynote is we also showed a demo, the N-Bodies demo. So since most of you, other than the 4 people, have seen that already, I'm not going to show it. So I was going to. I'm not going to. For the 4 of you that haven't caught that, the keynote was recorded so you can see that. Instead, I'll just give you a glimpse into another demo you may have seen if you went to the Parallel Patterns Library talk, which is this video recording. And that's what I thought it was when I first saw it. I thought this must be a video recording of the C, but it isn't. We're actually doing all of that in software. Isn't that amazing? So in order to compute and render this thing, you got to take various parameters in complex formulas, certainly beyond what anything I can understand, which takes into account the lighting and where that comes from. Takes into account the depth of the water, so how blue you show it, the distance, where the wind comes from, how far the waves are in order to render them correctly. So there's a whole bunch of computation that takes place here, and this is all taking place on the GPU using C++ AMP. And up in the top corner, some of you that have good eyesight will be able to see the number of frames per second we're getting. Anyone remember what the frames per second you got when you use multi-core? Anyone go to that session? 30, 35, and how much can someone say how much they can see up there? 160. So that's the kind of improvement you can get for using the GPU for computation purposes. And the only other trick this demo does, unlike the N-Bodies that had many tricks, is you can actually see how we're doing this. So every point here that intersects is a different calculation you have to do as to where it's going to appear next and with what color and so on. So that's all I'm going to show you in terms of a demo. And we can go back to the slides. So again, if you want to see the N-Body simulation, it was captured in a video in the keynote, so you can go and watch that video. So how are we going to spend our time here? Well, first we're going to set some context. We're in that section right now. We're setting context. And then that's going to last very little. And then we're going to go and see a lot of slides with a lot of code. So I'm just going to give you an introduction. I know you have not seen this technology before, so we'll just go very simply through what the API looks like, what the language looks like. And then in the end, we'll have some closing thoughts, and I may share a couple of things that I hadn't shared before, so there's a reason for you to stay right till the end. So that's how we're going to spend the time. Is that OK with everyone? I guess this wouldn't be OK if you're not a developer. If you're not a developer, you're not going to like a lot of code on slides. So, but before we get there, let's continue with the context. So today, there are many domains where people write software to take advantage of heterogeneous hardware for computation purposes. Anything ranging from astrophysics to research on genes, to volumetrics, linear algebra, the finance space, ultrasound, you name it. A whole bunch of domains are benefiting already from using the GPU to accelerate their applications. And they're seeing speedups, according to these numbers, anything from 17 to 149 times faster than if they weren't using the GPU. And I guess you all know that. That's why you're at this conference. But when I first saw that, the question I had in my mind as a newcomer to this space was why? Why are we getting the speed up from the GPU? And invariably, people that try and answer that start from the hardware. And you get a lot of talk about how the hardware is different and try to explain it that way. So I've heard a lot of explanations starting from the hardware, and I've captured some points of the differences between the CPU and the GPU today on this slide. But ultimately, if you look at it as a software developer, what does it mean to you? And what I found it means, and I'll just share that for those of you that don't know, is you're still going to write a CPU application. It's not like your application entirely runs on the GPU. The operating system is not going to run on the GPU. You're not going to make system calls, load DLLs there. Your threads don't have a call stack. So it's a kind of a limited world where you still write the CPU application, but parts of your application, where you have a compute-intensive and ideally a data parallel algorithm, those parts you can offload to the GPU, and it's much better at doing that. So it's only small parts of your app that will go and execute on that. OK, so why is that going to run much faster? Well, that's because the GPU, again, from a software developer's perspective, in simple terms, there's just a whole bunch of threads, thousands of threads, think of it that way. They all run at the same time, executing the same instruction with the only variable being the data. And they're just very good. The GPUs, these threads, these cores, are very good at crunching numbers. Right? They're not as smart and as good as many other things like branch prediction and so on that you have on the CPU, but they're very good at doing that. So if you can find a way to take an algorithm from your CPU program and offload it, execute it on the GPU, and you have a lot of data, a lot of number crunching, then you'll benefit and you'll get the performance improvement. OK, so that's great. So how do we do that? Well, the way that you do that today is I write my CPU in a mainstream programming language, whatever your choice is, and then I go and use these niche, exotic, C-style other programming models in order to get this performance gain. So for relatively small parts of my application, I have to use a whole new tool set, new compilers, new syntax, and try and integrate that with my CPU environment to get the benefit. So that is kind of painful, and that's where Microsoft has stepped in to try and address what we think is an issue there if we want to bring these capabilities to the mainstream. So those are some of the differences with CPU and GPU today. But when you go and look at what's happening tomorrow, I mean, you've seen all the announcements here with the APU, bringing things closer together. And of course, Microsoft has close partnerships with all the hardware vendors. There's a lot more that's going to come out in this space. So we were in a unique position to design a solution that doesn't just work for today, but has a future-proofing inside it for hardware that we haven't even seen coming from the various hardware vendors. Of course, I'm not going to talk more about the future here. This is about today. So every time you hear me say GPU, think about just accelerator or some hardware device that has data parallel capabilities. But we'll focus on today. So this solution that I'm talking about is what we've announced, which is called C++ AMP. We've covered that already. And it is part of Visual C++. So it's part of the same mainstream compiler. It's the same mainstream language. It's the one compiler that works for both your CPU and your GPU code. It is well integrated into the Visual Studio environment. So you're debugging, you're profiling, you're editing. It's one ID, one set of tools to learn and use for both your CPU portions, the majority of them, and part of the GPU that you're going to be offloading your computation on. What else is it, at the high level? So it offers an STL-like library that lets you deal very easily with really large, multi-dimensional data in a way that exposes parallelization and they can run on heterogeneous hardware like the GPU. And what we're doing is we're building on DirectX, or also known as Direct3D. So we're building on a technology that is ubiquitous. Every Windows box has that. And it's also reliable through the very rigorous Windows certification process. And that gives us the hardware abstraction. So if you look at the what here, you can think of what the benefits really are. So one benefit, of course, is performance. We let you very easily take a data parallel algorithm and run it on the GPU. So if you have large enough numbers, you're going to get the performance you want out of that. The other is by using your existing skills, your existing assets, you're going to get productivity. And that is key. And of course, by building on a hardware-agnostic platform such as DirectX, you get the portability. And every time throughout this presentation in the coming months, whenever you have a question of why did they do that like this in C++ AMP, you'll be able to trace back the decisions back to these three benefits, which were also our guidance as we were designing this solution. Those were the three things that were guiding us. So that's kind of some meta information about C++ AMP. And that really ends the context. That's all I wanted to give you at this stage. So now we can go and look at what it looks like. Are you ready for code? Yeah? Good. I'm seeing the nods. So the simplest code I could write. It's not the most elegant. I could have done different things here. I could have used vectors. I could have used const instead of what I'm doing. But I just stripped it down to the bare minimum. So what does this code do? It just does an addition, right? So we take this code, and how can I write this in a way that is going to be parallel and can execute on the GPU? Think in your heads, maybe with the existing solutions that you are using today, or if you're not using any, how would you like this to just work on the GPU? And just picture that. So what I'm going to do is I'm just going to insert some spaces and copy it to the other side. So we're ready to transform this into the GPU code. So check it out. We're now going to make this run on the GPU. And that was it. That's the delta. Now, I've shown this internally to some people that were not familiar with the technology, and there were a few comments that came out. So in case you're thinking the same way, someone said, oh, OK, so that must be your device code. Where's your host code? This is all the code. Someone else said, so what do I have to change in terms of environment variables, project settings? Nothing. You haven't had to change anything in the compiler. You just added some more C++ code where you had C++ code. You compile, and now this thing is going to execute and take advantage of the GPU. It is that simple. So at this point, we can go and dive a bit deeper into what do these things mean that are up there. So let's take this in the front and center and start looking at some of the elements that will be new to you. So we have our entry point, parallel for each. So this is just a method call that takes two arguments, the second of which is a lambda function, which is the thing that's going to be executed on the GPU by the number of threads that you specify in the first argument, which is the grid. So the grid describes the shape and number of threads that are going to execute the lambda function, which is the second thing you pass in. And then you'll see on the lambda we have this new restrict direct3d, and we're going to cover that later in more detail. Basically, what you're doing there with that annotation is saying this code should be able to compile and run on the GPU. So you're indicating to the compiler your intent. If you then go and look at the lambda, it takes as its first argument an index. So this is a new type, and you can think of that as your thread ID. So that is going to be, as your code executes, you'll be able to use that as the only variable thing that's going to come into your code. You can use that to index into some data. But you never explicitly passed any data here. That's where the array view comes in. So the array view was declared outside of your parallel for each, and all it does is at this point wraps the data that you have already in your program. So you wrap that around your existing data, and when you use it in the lambda, it gets captured there with normal lambda capture semantics, and you can use that, and then the data would be copied to the GPU and used over there. And then the lambda body just goes and does its computation, and at the end of this function, you'll be able to, when this function returns, you'll be able to access PC, which will have the results in. Or if you want it after the parallel for each, you could just use the sum array view and look at the data. Is this fairly straightforward? Some nods, some people not nodding yet. Maybe you'll nod later. So what we'll do now is, this was kind of in a nutshell, and now we're just going to go and drill further into each piece so we can get more nods. So the first thing I want to start with is by looking at three elements. So forget GPU, just three new classes that we're adding here. So we're offering in this STL-like library an index, which represents the n-dimensional point. The underline type there is a 32-bit signed integer. And all that does is you give it a dimension, let's say 3, and then you'd pass in 3 numbers, and it represents a point in space. There's nothing else about it. Fairly straightforward. Then we have the extent n, which represents the number of elements in each dimension of an array. This is not the array. This just represents the shape of what a multidimensional array could look like. So again, you give it how many dimensions you want, and then you give it the 3 numbers, and that's how many elements are going to be there in each dimension that you want to have. And then we have something called the grid, which is really just like the extent, except it has the ability to have an origin that is non-zero. And the way that you'd give it that origin of non-zero is using an index, because it's convenient. It represents a point in time. You can use that. So a grid is nothing more than an index and an extent. And that's what it is. And we'll see the purpose it serves later on. And where I say n here, n can be any number. So this is not just 1 dimension or 2 dimensions or 3 dimensions. It can be any dimension you want. And I mentioned this to someone the other day. I said, you may want to have 5 dimensions. And he said, if you want 5 dimensions in your code, you're doing something wrong. And maybe that is true. I don't know how many people use more than 3 dimensions. But I've heard in string theory you want to use a lot more. So if you're a string theorist, we let you do that. You can have your 12 dimensions here, and you'll be happy. So those are the three types that I wanted to quickly talk about. Let's see them in action, make sure they really resonate with everyone. So here you're seeing an example of one dimension. So we have a one-dimensional description of 6 elements. So how do I do that? I say extends, pass in n as the template argument, my variable e1, and say 6, and that tells I want to have 6 elements. And then this is, again, not the data, just the shape. Imagine if I gave that to some array, constructed an array with this argument, then I'd be able to index into it. And if I wanted to go to the third element, I'd create an index. Again, I say it's a one-dimensional. The variable is I1. I pass 2, and now I've just indexed. I can access the third element. Fairly straightforward. And then if we look at the multi-dimensional, the two-dimensional case, again, in this case, it's a 3 by 4. So I'm saying extend, say 2 for the 2 dimensions. My variable is E2, 3, 4. And the thing I want you to notice here is that we go YX. And then in the third case, you'll see we go ZYX. So the components, we go from the most significant to the least. So again, you look at the index, how we access that. So the index and the extend, you can see the correspondence. How many dimensions you say in one, you say in the other. You pass in the integers. It's fairly straightforward. Right? OK, so how would I create grids from this? Well, if I wanted my grid to start at 0, it's fairly straightforward. I say grid of 1, my variable g1, pass it the extent, and we're done. If I wanted to actually have a grid that has the same shape as, let's say, as the last one, the 3-dimensional shape over here, and I wanted the origin to be something other than 0, let's say like that, then I'd create a grid like this. So I'll say my grid, 3 dimensions, variable g, pass in an index with 3 dimensions, and the actual coordinates I want to start from in the ZYX order, and then the extent of the actual shape. And now I have a grid that is like the extent, but with a different origin. And of course, you can use negative numbers here. So if I wanted something that starts at -1 all the way to 98 on all 3 dimensions, I'd create it like this. Is this easy? Someone said no. Who was it? It's not easy? OK. OK, feedback noted. We have to put pictures in the compiler so we can understand it better. Understood. But now with the pictures, do you understand it? Somewhat. OK, we'll see if we get more of that in the towards the end. OK, so it doesn't look like something you would parse. That's good feedback. For everyone else, I don't know if you have the same comment. There's a question? It's a template, so you have to declare what you want. So, and I'm not going to, I'll take questions in the end. I just wanted to make a check. And I'll give you my email as well, so you can ask more questions later. So we have the grid extend and index, which for some people is not humanly parsable. For some others, like, yeah, that's straightforward. That's life. Yes, variety. But what do you want to do with these things? What you want to do with these things is, of course, use them with data. And we give you 2 ways that you can actually store your data: an array and an array view. So if we look at the array first, so an array, again, uses templates here. So we've got the t and n. So t is where you're going to say what your type is. So for example, int, if you want an integer. And then n is where you're going to say your dimension. So you could say 2. So now you have a 2-dimensional, you have a matrix of integers. And you can see that's what we're doing down here. So let's look at this code. So here we have, let me use the mouse so you can all see what I'm reading. So we have here a vector of integers. So it's going to have 96 elements. But in reality, this is an 8 by 12. So what I'm going to do is I'm going to say, OK, give me a 2-dimensional extent. The variable is going to be, and then I'll give 8 and 12. So y first, x seconds. And if I wanted to access those components, it would be as the comment shows over here. So now I've got my extent. I can go and create an array. So I can say I want an array that's 2-dimensional of integers. And then I'll pass in the extent that gives that array its shape. And then I'm going to go and pass. I could just pass v, but I can also use the iterator syntax here and say v begin, v end. So at this point, what I've done is I've created an array on the GPU, which has this data. The copying has taken place using this particular type. Then I'm going to use my lambda that I showed you earlier and we'll talk about later on as well. So imagine a parallel for each somewhere here. And then in my lambda, how would I use this? Well, if I wanted to access the colored square, the value of that, I would say give me an index of 2. So it's a 2-dimensional index. And then we pass in 3 for the y, 9 for the x. And now we have our index, I. And now I can go to the array and say, hey, sub I, and I can get back the results of the variable. So fairly straightforward, I hope that is, except for you, everyone else can answer. But no, I'm only joking. I'm just going to show you here that we could have used here different syntax. So in this case, we've overloaded the subscript, so it takes a two-dimensional index, and that's how you get into that exact point. Very convenient for accessing data in multi-dimensional fashion. But if you wanted to, you could go directly and say I.y, I.x. So we have specializations, a convenient specialization for the first 3 dimensions. So you can say z, y, x and access those things from the index, the extent, or wherever. You don't have to use the other form, which is this one here. And that's how you get the 0th and the first element. That form is useful when you have more than 3 dimensions, for example. I'll take questions in the end, but I'm curious because you put your hand up now. So what is it?
Well, you keep mentioning copying of data. So I'm wondering, like when you are passing it to Lambda, are you copying?
I'll cover that. Yeah. So just to repeat here, in this example with the array, when I created the array, at that point, I have the data on the GPU with the array. So it's gone to the default GPU that we've picked for you. We'll see now that if we go to and look at the array view, it's slightly different. So with array view, again, a similar example here. We have a vector, and so we're saying here there's a vector of integers, and it has 10 elements. And again, this in reality to me represents a 2-dimensional thing. So I'll create an extents of 2, variable e, 2, 5, and then I'll pass that e to my array view. Here I've used the alternative syntax. We have various different ways of doing the same thing. So depending on your background, you'll use one or the other, and it'll just work for you. And here I've just created an array view. Now this array view has not gone anywhere. So at this point, it's just a wrapper pointing to your data. You can think of it as an alias thing if you want. So the moment you capture and use that in your Lambda, and your Lambda executes on the GPU, that's when we'll take and copy it. So it's an on-demand implicit copy that happens for you when you use the array view. That's the main difference between these 2 types. And I just want you to notice that I could have created the array view, as I did in my original example, in fact, like this. So in this example, I'm just passing 2, 5. I don't have to create a temporary extent. And in most scenarios, you don't have to create the extent explicitly. You can, but you don't have to. You can just create the array view like that, and it will internally create the extent for you and do the right thing. The other thing to note with array view is that you can actually, and it goes back to the copying thing, you can use it and tell the compiler how you want this array view to be used, and that's going to help you performance-wise as well by saying const, for example, before your element t. So before int, you can say const int, and then you're saying, I want this to be copied in, but I don't care about it being copied out, so we won't do that for you. And we've also introduced the write-only, so you can go and use write-only and wrap that around your int again or your float. And then what you're saying is reserve storage for this on the GPU, but you don't have to copy it in. I only need the results, so you only need to copy it out. So when you use array view, you get the flexibility of on-demand implicit copying, and you get the ability to specify exactly what you want to happen with your data. Yes, so you cannot pass pointers here. And I'm going to talk more about restrictions later down. And again, that's one way of bypassing, by throwing the question out without putting your hand up. But if you can keep them for the end, that would be great. So if you compare these 2 together, you'll see they have many similarities. So the rank is determined at compile time in both cases, the extent dynamic at runtime. They're both rectangular. The array is dense. The array view is dense in the least significant dimension. And the other difference here is that the array view can have an origin that is non-zero, so that's a benefit of that. And like we've already examined, array is a container for data, whereas the array view is just a wrapper for data. So by default, and especially if you're thinking for future-proofing, when no copying will be required, the array view is the safer way to go. The array, in some special conditions, can give you some performance advantages. I'm not going to cover that in this talk. But by default, I'd say you use array view. And only array if you really think that you need to do that. So that's just in a nutshell the data comparison between the two classes. So let's go and see the main guy, which is the main entry point parallel for each. So everybody will be using this. So like we said earlier, parallel for each is just a method call. So it starts on line 1 and it ends on line 1. That's not a typo, I put that on purpose. So that's where the parenthesis is open, that's where they close, and you see the semicolon. The first argument is a grid. We all know what a grid is now, and that's on line 2. And then on line 3, you see the lambda. Now, how many people here are comfortable with lambda functions? Can I have a show of hands? Okay, that's many, but not all. This is something that is part of the C++ standard. It's been in our compiler since the previous release. It's been in various other C++ compilers as well. In a nutshell, these are not as scary as they look. When you see something starting with the open, closing square brackets, you've got a lambda function. After that, you'll see basically argument list. So this is not written correctly here. You have index n, I. You need to say what the parameter name is. And then after that, typically you see the braces, and then you put your code. So you're basically, at this point, defining a function and passing it to this method. So the restrict directive is something we've added for C++ AMP, and I'll talk about that in a second. So here you're saying, take whatever code I have here, where I'm saying kernel code, and then take that, and that's the thing I want you to execute on the GPU. And what it's going to take is the index. Now, how are the indices going to be generated? This is another way of thinking of the grid. You can think of the grid as an index generator. By telling the grid what the number of elements are and how many dimensions and its origin, that's exactly the set of indices you're going to get passed into the parallel for each. And typically, there'll be millions, right? You get millions of threads in no particular order. And then you use that index in there to actually go and access the array or array view that you've captured into the lambda. So the other magic thing about lambda and the beauty of them and why they're so great here is this is what it gets passed in. But anything you have above here, above this line, there's a local variable, for example, you can just capture, you can just use in the parallel for each. And that's how we got to use the array views and the arrays earlier on. I'll have another example later where you'll be able to reconcile that. So an implementation detail here, so nothing to rely on, but just because I'm sure some of you are curious, what really happens here? So what really happens here is what we do is we take the parallel for each, which we've added in the library. So you use the amp.h, the header file, use the concurrency namespace, now you have access to all of this. So we take the parallel for each, and we say, OK, here's where you want to access the GPU. So what we're going to do is generate code. So we're going to generate HLSL code, high-level shader language, which is the language used. It's a C-like syntax used by direct compute, which is the subset of DirectX that allows you to target the GPU. So when you compile, we take that, and we generate HLSL code for it. We then take that HLSL code, and we generate HLSL bytecode for it. And then that's what gets into your binary that you ship to your customers. So then your customer gets the exe, and they run it. And when they run the exe, what happens to that HLSL bytecode? Well, it eventually ends up with a driver. So you have a DirectX 11 driver there from the hardware vendors, such as AMD. So you get the driver, and the driver takes that bytecode, and from that generates the hardware bytecode that's going to actually execute on the GPU. And it is in this manner that you don't have to ship any source code. You don't have to ship fat binaries. You just ship one binary with the HLSL bytecode in it that happened from here. And you never knew that, and you don't have to know that. That's just something that happens under the covers for you. The other thing that happens under the covers for you here, of course, is we don't just generate HLSL code here. There's some CPU-side code that has to be generated as well. The part that actually talks to the device sets it up in order to go and eventually dispatch that kernel that was written. So there's a lot of code generation happening here for you at compile time, and a lot of work happening for you, which is why this makes it so much productive for you to work in. You don't have to do that. Someone that doesn't know questions have to wait till the end. What is it?
I'm just wondering how you store the CPU code and the HLSL code together in the same binary.
The HLSL bytecode. Yeah. Magic. We store it. We own the bits. We can do whatever we like. So we've modified the actual C++ compiler, and we've done that. If you want to talk more about that, happy to talk later in a more serious manner. And in fact, I have many people from the product team down here. So after this, by all means, you can all come here and we'll have a big discussion about implementation details. But that's what this is. No, I don't think we changed the binary format. No, we didn't go that far. OK, so the other thing that you can see up there on the slide is that this code executes as if synchronous. So what does that mean? Well, in reality, it's not synchronous. You're going to another device. So when you invoke the parallel for each at runtime, it's going to fork off. The GPU is now busy running your kernel. Your CPU code continues. So after the second line one, you can go and do CPU code stuff. So you can process stuff on the CPU. Now, at some point, you want to access the results of that computation. It is at that point where the synchronization happens, so you can get the results back. So if it was all executed and you try and access the data, we'll copy it back at that point. If it's still executing, we'll wait for that to come back. If you want, and especially if you're using the array, you can go and do a copy async. So you can say, hey, I want you to copy this back, and then it gives you a handle that you can go and wait on later to get the results back. So there's various ways you can get the data back, but mostly we help you with that. So it's as if synchronous in terms of visible effects, not really synchronous. So the other thing that's on this slide that we haven't talked about much is the restrict direct 3D. So what is that doing there? So this is the one, really the one general language extension we've added. Everything else you've seen here is really library, right? So the one language extension is restrict. And this applies to functions, and Lambda functions are functions, so it applies to those as well. It's a very generic enhancement. So it's not really necessary to do something with the GPU. You could imagine in the future we say restrict, and we put some other word in there to do something in a completely different context. So this is just a good thing to have in the language. Now, what we've implemented to pass in there is just two things, CPU and direct 3D. And CPU, if you don't specify anything, which you haven't in all of your C++ code today, because you didn't know this was coming, it's by default, it's implicitly restrict CPU. If you put restrict direct 3D, you're saying, here, this piece of code has to be able to execute on the GPU, so make sure that it can, because obviously there's restrictions. So what kind of restrictions are there? So here are some of the restrictions. You can only call other restrict direct 3D functions. So from that Lambda, you can make calls to other functions, and they have to be restrict direct 3D. You could combine them. You could make a function be restrict direct 3D, comma CPU, and then you can call that one from the CPU as well. So you can do that kind of thing. Functions must be inlineable. And I'm not going to go through all of these, but there was a question earlier of could I have pointers in there. You can see the kind of types that you can have. So our restrictions, and there's more. Let me show you more. Our restrictions are basically the restrictions that are in the DX layer that we're built on. And those restrictions are in there because of the restrictions on the GPUs. So as the GPUs relax the restrictions, and they're definitely doing that, the DX layer will relax its and will relax ours. So you'll be able to do more in there. So that's kind of the way that this goes. The restrictions are because of the way ultimately the hardware behaves. And over time, you'll see these going away. Now, typically, your data parallel algorithms are about just number crunching a whole bunch of multidimensional data. So most of these don't really matter. But they're there for your reference. So at this point, we're ready to see one more example, because now you have a lot more background. So we'll go with the matrix multiplication example. So please stare it for a while, and then I'll walk you through it again. OK, so what do we have here? We have the same signature on both sides. We're basically taking two const vectors that we're going to multiply together and store the results in the third vector. Same on both sides. On this side is where I want to go and do the thing running on the GPU. So I've got to wrap my data. So I go and wrap it in an array view. I'll say const. So do the good practice here. It's floats. It's a two-dimensional array view that I need. And I'm just passing in here the dimensions that were given. And I'm creating A and B. I'm doing that on the same line. Then the results are going to be stored in, I wanted them to be in VC. So I'll wrap that as well in another array view C. And I'm saying write only, because I only need to reserve the space and copy it back. I don't need to copy it in at all. Then I go and do my parallel for each. So in my parallel for each, remember the first argument is going to say how many threads I want and the shape of them. So I could go and create an extent and then a grid. But like I said, we've made this fairly easy for you. So a common scenario, not always, but a common scenario is that the shape of the threads, the number, is going to be exactly the same as the resulting array. So in this case, in the array view, for every element, I'm just going to have another thread doing that computation. So that's why I just go to the array view and say, hey, give me a grid that I can pass here into the power for each. Fairly straightforward. Then the second argument is the lambda. So here in the square brackets, you can list the things that you want to capture into the lambda, the things you want to use. So I could have written here, I could have written A, comma B, comma C. And that would have been enough. I've just captured now those three. But just saying equals, I'm saying capture everything that's above by value. And then I can go and use whatever I want. This is just vanilla lambda stuff that you can go and read about on the web or wherever else you get your information from. Then in here we have the index, two-dimensional, to match the two-dimensional data I'm going to operate on. Then we have our restrict direct 3D. And then in there I have the body. Now the body that I've got in bold, if you look at it, it's the same body that I have on the other side in my serial case. There's one difference about this body. It is nicer. If you look at its indices that it uses, these actually make sense to a human because it's a two-dimensional index, whereas here I had to do some funny arithmetic because really the vector represented the matrix, but it was stored in a flat manner. So that's one of the good aspects of being able to have rich types to work with multidimensional data. And then the results are the same. So after here, when this returns, the distractor of C would be invoked, and I'd be able, on my calling code, to go and use VC, and I'd have the results there. And this would perform, at least 40 times faster on my machine back in the office. I'm not making any claim on performance numbers, but you can try this yourself. So that's just an example. Does that make more sense now than the first one? See, I want to see the nodes. I'm counting the nodes again between. This is the way we communicate. And yes, yeah, we can have audible communication as well. That's true. It's a small room. OK, so let's move on. What have we seen? So this is what we've seen so far. One new language addition, one entry point for actually creating the kernel that's going to run on the GPU, and 5 new classes that make it very easy for you to work with multi-dimensional data. There's 2 classes I didn't touch on. I just want to say just a few words about them, just so you know they're there. And that's accelerator and accelerator view. So far, nowhere did you have to say which GPU it executes on. Those of you that were the keynote saw me actually using a whole bunch of stuff and even 2 GPUs at the same time. So the way that happens is by using the accelerator and accelerator view. Those classes are useful for 3 main scenarios. One scenario is you want to check the capabilities of what you're going to execute on. So for example, maybe you have some algorithm that relies on double precision. So you can say, OK, let me look at the default accelerator. Does it support double precision? Maybe the only accelerator that's available on your machine is an emulator, and you don't want to run on an emulator. So again, it lets you check the capabilities of what's there, and then you'd have to take alternative course yourself, like implementing it on the CPU or doing something different. Beyond checking the capabilities, another usage is if you're doing a lot of DirectX interop, so you have HLSL pixel shaders and stuff like that, the accelerator can help in some of those scenarios for when you do interop, because you can use it as a device with the DirectX APIs. And the third is when you want to target more than one accelerator. So what you can do is you can go on the accelerator and iterate and get the results of all of them, or you can just go straight to the default. Or if you know the string that represents the actual device, you can pass it in the constructor. Various ways to get an accelerator variable. And then you can pass that to the parallel for each. There's an overload for that. And then that will execute on that accelerator. Another place you can use it is when you create arrays. Since arrays, like we said, at creation time go and get stored on the GPU, there you can also pass an accelerator and say, hey, create this array on that GPU, on that accelerator. So those are some scenarios where you can use that. I'm not showing you code for those. In most scenarios, you don't need to worry about them. You just execute on the best one, which we pick for you. Now there's more. This is what we've seen so far. Let me see how we're doing on time. We're fairly good. So there's more. What I've shown you here uses, for those of you that know how the GPUs work, the global memory on the GPU. We have not used any of the shared memory that you can use on a GPU, for those of you that are familiar with what's happening there. So let's go and have a look at what we need to do there. We have a few more types in our programming model that allow you to fall below to that level if you want to go there to achieve the maximum performance. So on the GPU, threads are not scheduled in the way that you have seen. So you can pick, like I said, any dimension, 5 dimension, and you just schedule all of those threads. What we have to do is map that into the way that the GPU really expects threads to be scheduled, which is in a different way. We allow you to go and specify that different way. And when you specify that different way, then you also have access to the shared memory that's on the GPU, which is 10 times faster to access depending on the hardware. So you want to do that if you're doing a lot of interaction with the global memory from your kernel. So how does that work in our programming model? So parallel for each has another overload that instead of a grid n takes a tiled grid. And instead of the lambda taking an index of n, it takes a tiled index. And you can go up to 3 dimensions here. And it basically makes the grid look like that. So if you look at the picture I have, the grid that we've seen without the extra partitions is what we've been using so far. You can further partition that into what we call tiles. And then in each tile, you have a tile of threads. So in this example, I would have 4 threads in each tile. Those 4 threads can share memory between them. That's the memory that's really fast to go and access. So what you could do is write your kernel in such a way so it goes and copies each tile, brings down from global memory the memory it really is going to be operating in the real algorithm, stores it in that tile static memory. If you think about it, that's what it is. It's for that tile of threads is static. And then accesses that in the actual algorithm. So let's talk a bit more about this. This is how you would create it, so some code. So I've got here an array view, 2-dimensional of integer. I called it data. I'm not creating the extent explicitly, so it's an 8x6, as you see over here, and it wraps some PMI data that I have. Then I go to the parallel for each, get my grid from the data, and what I want here is a tiled grid. And I can get that by calling the tile method on the grid. and passing it here as template arguments exactly what I want the tile to be. So in this case, 2 by 2. So now I've divided my outer grid into little 2 by 2 blocks, as you can see on the picture. Then I need to have a tiled index. So again, you know the index always matches the grid. So it's a tiled index 2 by 2, which allows me in the body to go and say tiled index global, and that gives me the global index to this point, for example. And this is what we could do before. But there's more indices here, because we've now partitioned things. And you can get those indices by going to the tile index and saying, what's my local index within this tile? You can get the tiles index overall. So this particular tile that this element belongs to is the 0, 1, 2, 3 down, and 0, 1 across. So that's what that would return. And then you can also get the tile's origin cell, its global index, by going tile origin. So okay, you can get a whole bunch of indices and use it in your code. What else? There's 2 more types. One is the tile barrier. So from the index, you can get a tile barrier, and then you can wait on that. What does that do? It says all the threads that are in this tile, when they reach the barrier, keep them there until all of them have reached it, and then let them loose on whatever follows. So that's a fairly simple concept. It's a barrier. And then the other one is the tile static storage class. So what do you do with this? In front of your local variables in the kernel, you put tile static, and that says this variable is going to be shared by all the threads in my tile. Right? So then whenever every thread sees the same value for that. OK, so time for the example here, and I'm not going to walk you through all of this. Some of you are thinking, thank God you're not going to walk me through that. Some of you are thinking, oh, no, I really want to see what that is. And that depends on your experience in this space. I just want to point out the pattern. So, and I don't know how you can see that in the back. I could earlier, but I've got good glasses. So what you do is you take your kernel that you have on one side. So here I've written it using the non-tiled model I've been showing you so far. And then on this side, I just go and declare at the top a static constant, which is my tile size. Then I go and call tile to get actually from the grid my tiled grid. I change the tile index. And what I'm doing here in the loop, you can see here tile static for lock B and lock A. This is where I'm going to the global memory and copying down for each tile once the data that that tile is going to operate on. Which means that later, after my barrier where I've synchronized, I've copied all the tiles down, I can go and run almost exactly the same algorithm. That's why it's got some black and some red in it. If you're colorblind, I apologize. And then what you see here with the red is I've changed the upper bound to be the tile size, and I'm accessing the local data rather than the global. And this is going to yield better performance results. Not all kernels will benefit from tiling. So I would always start with the non-tiled approach, see what performance benefit I'm getting, and if I want more and think I can get more, then drop down to the advanced tile model. For example, that Ocean demo I showed you at the beginning doesn't benefit at all from tiling. And you can understand, if you're going to global memory once in your kernel, what's the point of going once to copy it and then to use it? You might as well just go once. So not everything benefits from tiling, but many examples do. So we decided to give you that level of flexibility, even though we're giving you a higher level programming model anyway. So with that, we now really have seen all of the API surface that is in C++ AMP in the current bits that we have in-house, because we haven't released this yet. We're open to feedback and may add or change things. So I hope you agree that when you look at this API, it is a minimal API. We've added very little to the existing C++, modern C++ with templates and lambdas, and that gives you the access to the GPU without you having to worry about how you talk to each GPU, without it being a single hardware solution, and with having all the productivity in there. That's the code I was going to show you. Is that what you were expecting? Yeah? Great. So closing thoughts. I did not show you here explicitly, without going into the reasons, Visual Studio in action. When you see Visual Studio in action, I can guarantee you're going to love it. If you don't love it, you can email me at daniel.moth@microsoft.com and tell me why. But at this point, I'm not showing that. I can show you a teaser of our profiler that does a great job of showing you the performance characteristics of your application, both on the CPU and the GPU side. And I can also show you a teaser of our debugger, if you can see that, which is the parallel debugging experience, again, enhanced on the CPU, and all of it available for you on the GPU. We'll be talking a lot more about the Visual Studio integration in the coming months. If you want to see more of this and actually give feedback to it, there is a usability study that's run around the corner. So you go out, go that way, then turn. And you'll be able to go and see the profiler there. And you can also look at the API that I've just shown you, see some examples of that, and give feedback. Because we're still open to feedback to change things, tweak them as you see fit. So, in summary, I think I've got 20 seconds. I'll take a minute if that's okay. Democratization of parallel hardware programmability, and some Greek guy on the slide. I had to do that because my accent comes from Greece. That's where I come from. So I had to put that on my slide. So if you don't like that, I'm sorry. So what we've done here is really we've lowered the barrier to entry for developers to take advantage of heterogeneous hardware. And hence, we're bringing performance to the masses. We've done that in C++, the language you know, in the compiler you know, with minimal API additions, integrated into the award-winning, leading-edge Visual Studio development environment. I really believe that. And that means that you don't have to sacrifice your productivity. And we've built on a hardware abstraction platform that allows you to target hardware from multiple vendors today and future-proofs your investment for hardware that's yet to come in the future. And thus, you don't have to compromise your portability. So it is what I said earlier. It's performance, productivity, portability. And as you heard earlier in the keynote, and I'll just repeat it here, we intend to make the C++ AMP specification open, and we will allow and encourage other compiler vendors to implement the same thing in their bits. And I think that is just awesome news. So with that, thank you very much for staying throughout this talk. I hope to see you sometime in the future. And if you have any questions, you can email me directly, or you can follow this story as it evolves on my blog. Thank you very much.